Okay, great. Yesterday we talked about five EAS reactions. Hmm. You know that as electrophilic aromatic substitution, that's in order halogenation, nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts um, acylation. So, for instance, if I have benzene, and let's do nitration, HNO3, H2SO4, just put a nitro group anywhere on the ring. And whether you put the nitro group at the 12 o'clock, 2 o'clock, 4 o'clock, 6 o'clock, or wherever, it's the same product. But there's an issue when you already have an existing group on the ring and you want to do another reaction. So, for instance, if I want to do a bromination, Br2, FeBr3, what products are we going to draw? Because depending on where you put the bromine, you're going to get different constitutional isomers. So in one of the videos, or maybe two of the videos, I talk about analyzing that group, and I call it the good, the bad, and the ugly. If this is a little bit um, unknown, or if you haven't watched the videos, I'll try to summarize it here. But you want to evaluate whether that group, the group that's on the ring, not the group that you're adding, but the group that's on the ring, is it good, bad, or ugly? For those of you who maybe ask your parents, or these days, at this time, maybe your grandparents, if they remember the movie The Good, Bad, and Ugly. um, this eventually, when we have competing groups, when you have maybe two groups, and one of them is good and one of them is bad, the good always wins. Or if one of them is bad and one of them is ugly, the ugly will win. Okay, so they're actually out of order. But the good, it's normally electron donating group. Okay, so that's the chemistry that you need to be familiar with. What groups are electron donating? What groups are electron withdrawing? And I'll get to that. I have a couple of tricks on how to memorize that. Bad groups are typically what electron withdrawing groups. Okay, pulling electrons away from the ring. Pulling electrons away from the ring. Ugly is a little bit tricky because it 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 makes the benzene um, act like it has a bad group on it. It becomes less reactive. So bad, maybe I can put electron donating groups, and they activate ring, and they electron withdrawing groups deactivate. Hopefully you can see that. It's not too far to the right. What I mean by activate and deactivate is the speed of the reaction. Does the group slow down the reactivity of benzene, or does it speed up? So the base, or we're always relating it to just plain benzene, we have that reactivity for bromination. Does putting a nitro group slow that bromination or speed it up? The reaction will still happen, okay? Even if you have a deactivating group for almost all of these reactions. There was one exception. We'll get to that also. So for the ugly groups, deactivate, but where you put the group is more like if there was a good group. So it's a combination of both of these. That's why we call it ugly. Um, don't worry exactly how we consider it. It's really considered an electron donating group. but it's deactivating. But don't worry about that. Let me get to the answer here. This is considered a bad group. And the skill that you need to acquire is, can you categorize this group and can you tell me how it's going to direct the incoming electrophile? So these are called directing effects. And that was the title of the first video after class. Okay. The video during class is video A. This is video B. Okay, directing effects. So let me tell you now, and then we'll go over why. But this is a bad group, and I'll put a reminder to myself, B with a circle. Bad groups direct the group one carbon over. So the relationship between the two groups is going to be a 1, 3. 1 and 3. Is that right? 1, 3. Just double check my work, those of you who've watched the videos, if I'm saying anything different or out of line. The 1-3 relationship is called meta. If you want to memorize this is ortho, meta, para. Going the other way, this is ortho, meta, para. In the videos, I discussed why bad groups are meta directing. Okay. Before I go over, and it will be meta directing no matter what you do. If you do sulfonation, it will go in this position, meta. If you do another nitration, it will go meta. Right? It's really based on this group, not based on what you're adding. Okay. Now, let me go over an example for each of these. Okay, one example for each, and let me discuss why I consider a good group electron donating and why I consider it activating. And I have two specific examples in mind. Okay. The first example is if I have this existing group. The existing group is going to be an amide. Amide. You've seen this before. Okay. Maybe towards the end of the review, I'll show you how to make this. Okay, because there will be maybe 20 points of synthesis. Okay, maybe 25. Some of the synthesis will be very simple. Some of them will be a little more drawn out, a little bit windy. But let's take a look at this. This is a good group, and it's electron donating. We saw that, I have to draw this on the side. We saw that if you have a ring, benzene ring, and you have an electrophile, the mechanism is this. The mechanism is the pi bond attacks. Pi bond attacks. So if your group, let's call it X, if your group is electron donating, you're making this ring electron rich. Okay? I'm not going to draw an arrow here. I was going to draw a dipole arrow, but let's not do that. But if you're pumping in electrons into the ring, that's electron donating. And if you're pumping in electrons into the ring, it's more likely to use one of its pi bonds to attack the electrophile. So you want the ring to be electron rich. And how do you make the ring electron rich? You add an electron donating group. Electron donating group. Okay. So why is this electron donating? Okay. Let me just write here. If ring is electron rich, okay, via an electron donating group, maybe, then ring is more reactive. more reactive. So that's considered activation. Activation. And we're going to discuss why this is electron donating. Okay. Here. Okay. It's electron donating because I could pump in electrons into the ring by doing this resonance. I have a lone pair there. I'm just checking the chat just in case. Oh boy. Okay. And the lone pair can do this. Make the double bond there and push electrons there. So your result in this resonance is this. I hesitate showing you this resonance because this resonance is never going to show up in a mechanism. This resonance is just explaining why this amide is an electron donating group. Because look what we have here. We have literally a negative charge there. Okay. When you do the attack, you're using just the benzene ring. Okay, there could be the group, but you're using the aromatic ring. You're not using this resonance. Again, this is just telling you why this is electron rich. We want electron rich, right? We want electron rich to be to be to make the ring more reactive. So I'm not explaining this. This does not explain really why good groups direct ortho and para. Okay, that's a related story, but a different story. I just want to clarify why I think something like this is a good group. Now, those of you who are still yet to watch the video, and actually those of you who've watched the video, you're given a list of good groups. So what example did we just do? We did this example right here. Okay, this example right here. But you notice that almost all of the good groups have a lone pair on the atom next to the ring. Because if you have that lone pair on the atom next to the ring, you can pump in electrons into the ring, make it electron rich, and make it more likely to attack an electrophile. The only exception are these alkyl groups. But these alkyl groups donate electrons not via resonance like these atoms, but alkyl groups donate electron density via hyperconjugation. And I tried to explain that a little bit down here when we talk about carbocations, right? That's hyperconjugation. So it is donating electron density. It's just not able to do it by resonance because there's no lone pair. No lone pair there. Okay. I think most people, when they think about the good and the bad, they pretty much understand the good. What about the bad? In contrast, we're deactivating the ring. So we're going to put an electron withdrawing group, so it's less likely. It will still happen. It will just happen slower. Okay? Let me show you that example. That example is also going to be an amide. But what's the difference? The difference is now I have a carbonyl group next to the ring, not the nitrogen. This carbon is partial positive, okay? But, okay, if I think this is an electron withdrawing group, right? This is now going to be an example of the bad electron withdrawing group. How do I show that? Well, I show that with resonance again. Because there's a resonance structure that pushes these pi electrons up to the oxygen. That makes this carbon positive, and we can draw electrons away from the ring. You see how this is now going in the opposite direction, away from the ring. Again, this is a resonance structure that you will not draw in a mechanism. Okay, we did mechanisms yesterday. We never drew how should I say this? We never drew a benzene ring with an electron withdrawing group and its resonance. The only purpose for this is to just prove that groups that have a carbonyl or groups that have like a carbonyl, like an N-O bond or a sulfur-oxygen bond, those groups are typically electron withdrawing. And this is the resonance structure that results. Did we really make the ring electron poor? See, there's a plus charge there. So while this one's electron rich, this one's electron poor. Let me do this in red, electron poor. Okay. Both rings will undergo reactions. It's just this one up here reacts a lot faster than this one. Okay, so you can do brominations on both of these. Now, I know I haven't talked about a lot about orthometa para. Let me complete that. And then I have one practice problem that I think will be useful for you all. So if I have this, let's go back to the electron donating group. There's your electron donating group. And I want to do, let's continue with bromination, or maybe chlorination, FeCl3. Okay. Again, what you want to do is you want to evaluate your group. Is it a good, bad, or ugly group? So this is a good group. And the key point is, or the key tell is that the atom next to the ring has a lone pair. What do we say about good groups? In the video, we said good groups, right, electron donating, are ortho-para-directed. Okay, so this is the next step. Once you realize that you have a good group, okay, you know it's reactive, or more reactive than benzene, but it's ortho-para-directing. Ortho position is here, and the para position is down here. So yeah, you are chlorinating at those two positions. There's the ortho, and the para is. So I know I'm going a little bit fast. This is being recorded, and I'll post the notes also afterwards. But you could test yourself, right? Just cover this up. Ask yourself, what is the product? Okay. All right. And the measure is going to be the para, just based on sterics. Okay. It's a lot harder to put something on this carbon because of some blockage. What are we going to do next? Let's do chlorination on this group right here, on this molecule right here. Unfortunately, I can't get this on the same page. Start a new one. Electron withdrawing group. So the electron withdrawing group that I have is this. It's the amide, but now we're on the carbonyl side. Carbonyl side. And Cl2, FeCl3 again. For the bad groups, meta-directing. Meta-directing. Okay. On the video, I did explain why. I'm probably not going to have time today to explain why, but that's all in the video. What's important here is that you draw the right product. The why can be learned from the video, but it's meta. We just said that's meta directing. So, what do I do with this? So this is a classic problem where we have two rings. You see what I'm doing? I'm combining the rings that we already had discussed. See, I'm combining So where are we? I'm combining this one, and we know what happens there, with this one, and we know what happens there, into one molecule. When you see a reagent and you see a problem like this, I think I'll try to specify the problem, but you are only doing one reaction. When you see a situation like this, I'm testing whether you know which ring will react, or which ring is more likely to react, and where is it going to react. Okay? So if you do your analysis on this ring over here, it's on the carbonyl side of the amide. So you're going to consider this a bad group. You're going to consider this ring deactivated. But this ring is next to an atom that has a lone pair. So this is the good group. So this ring is going to be activated. So we already decided, I hope you see that we've decided that we're not going to do the reaction on this side. It happens, right? This benzene ring is on the carbonyl side, so eventually we will chlorinate it. But when you see a problem like this is the one time where you assume that you only have one equivalent. Okay, don't assume excess. Don't assume that you're going to chlorinate in all the possible places. Okay, this is the ring that's activated. So now you're going to decide, where am I going to chlorinate? You're going to chlorinate in the ortho and the para. You see how color coding also helps me? I'm ignoring this ring now. You're going to monochlorinate these molecules. But because the good groups chlorinate or do the reaction on the ortho and the para separately, you're going to have to draw two products. Both going to be monochlorinated. So the ortho is here, right? Plus the and the para. The para is here. Yikes. Major. This is difficult. Okay. I understand that the material is coming fast, but this is difficult probably because you got to get used to knowing what a good group is and what it does. It directs orthopara. What is a bad group? Bad group we were looking at was this one here, the amide. But these are the other bad groups. With these other bad groups, you can draw resonance that shows electron withdrawing capability. For this one, you can't draw resonance, but you could draw a dipole arrow going away from the ring. So I'll just say it. So if you have something like this, let's just see. Why is this very electron withdrawing? Because you have all of these fluorines that are electronegative. So if there's some way that I could show this, I can't show this with resonance, right? I can't make this a double bond, but I can at least show something like this, dipole arrows pulling electron density away from this ring, making this ring electron poor. Electron poor. That's what we wanted. Or that's what you have when you have electron withdrawal, which is electron poor. All right. Let me try to talk a little bit about synthesis. So, yeah. There's several topics I want to get to. Let me go through side reactions. Side reactions are going to be very important for synthesis, okay? Because in Unit 14, we have those 5 electrophilic aromatic substitutions, but we could do other things. So an important side reaction could be this one. If you have an alpha group here, okay, an important side reaction is oxidation. K2Cr2O7, H2SO4. Why is this useful? Because this is a way to get a carboxyl group onto the ring. Oxidation. Like these are unit 13 reactions. At the time, we didn't realize what the utility of these reactions are, but now we do, because you can't put a carboxyl group using any of those 5 reactions that we learned yesterday. You could put an alpha group on a benzene, but then you would want to oxidize it. How about this one? NBS. Why is this interesting to put onto the ring? So NBS, is bromination at the benzoic position. Okay, this is literally a reaction that we saw in Unit 13, but how do we use this in the context of what we want to do eventually, which is synthesis? Well, we could do elimination, NaOET. What does that do for us? That gives us a very useful alkene. And you have all your alkene reactions. I don't want you to worry too much about restudying, right, alkene reactions. But since we went over this in class, it would be nice to know that, oh, I could get to the double bond from ethylbenzene. Well, let's backtrack. How do we get ethylbenzene? So this is a unit 14 reaction, right? You have benzene. We added an alkyl group, okay, a very small one, so that probably there won't be any rearrangement. So this one would be Friedel-Crafts alkylation. You see how I'm building up syntheses now? I could ask you, how do you go from benzene to benzoic acid? You have to use a reaction from unit 14 and then another reaction from unit 13. See, heck. Oh, sorry. What can we do with this? This is recent history. We could have SOCl2. Why would this be important? Because you know that acid chlorides can make amides. So I could literally make actually this molecule up here. Right? Once I have that, you know how to make the amide? NH3. And we have this. We can start doing a lot of interesting things on that ring. Let's see. Oh, 2 more side reactions. This one I haven't really talked about. But let's say we do a bromination. Br2, FeBr3. What could I possibly do with this molecule here? Okay. Grignard. Any reaction that I mentioned here is a reaction that I think should be at your disposal. That you should be able to know how to apply this reaction in a synthesis. Because once I have the Grignard, you know all the reactions I could do with a Grignard now. Right? You could attack an epoxide, attack a carbonyl group like a ketone or aldehyde. I'm not going to get too subtle. Like I wouldn't ask you to react an ester, but you've done that before. So let's just do something really simple. Let's do an epoxide. Is that simple? Mm. Let's do a ketone. Maybe that's more simple. And we have this dot Did I do that right? 3 carbons. Hmm. There's one other side reaction. Super, super important. By the way, what what's going to be useful? Like really useful? Like for instance, going back to the simple synthesis, 2 reactions to the benzoic acid. It's these reactions that get you a molecule that you cannot get from the 5 electrophilic aromatic substitutions. These are molecules that you cannot get directly from bromination, nitration, sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylation, right? The 5 EAS reactions. That's why these side reactions are important to know. How do you get an amide? Heck, how do you go from this benzene all the way to here, right? You have to get an acid chloride, right? Just give me 1 second. Okay. There's one more reaction, side reaction, that's super, super important. Because here I can make a, here I can make a carboxylic acid, benzoic acid. How do I make aniline? If I have this benzene ring and I want to do, um, make aniline, you realize that there is no one reaction that can get me to this amine, right? Not bromination, sulfonation, nitration, Friedel-Crafts alkylation, Friedel-Crafts acylation. How do I do this? The only way that you could do this is to go through the nitro group. So HNO3, H2SO4, and let's put a nitro group right here. You'll need to reduce the nitro group. So again, there's no way to make this except through the nitro group. So this is unit 14. The unit 13 reaction is either iron with HCl and then NaOH. This is a reduction right here, and you're making NH2, but because you're an acid, you actually pronate it and make it NH3. So you would have to add base to get rid of that third hydrogen, make it neutral, NH2. There are other ways to do this. So I don't know if I caught all the ways. In the practice problems, you could use tin in HCl, and it would do the same thing that iron did. Okay? No mechanism, right? This is more of a radical mechanism. Or just simply H2 and platinum hydrogenation. You don't need NaOH if you do this. If you put NaOH, that's perfectly fine. So those are a couple ways to go from nitro to amine. Now, let me, what time is it? Let me do one synthesis, okay? And then I'll open up the floor to questions. Let me find one. So this is the practice problems that I've posted for Unit 14. And yeah, here we go. Here we have a couple of syntheses. Let us do, let's do that one. Let's do this one, okay? So let me copy this for us. Start with benzene. Throughout the semester, I've been advocating you do trial and error. Experiment. Try this reaction first, and then a second one, and see if you get closer to the product. Same thing for a mechanism. When you're first learning a mechanism, do trial and error. See, well, does this arrow work? Or for resonance, definitely you should be doing trial and error because you want to know what is possible and what is not possible. But for me, I mainly see what's impossible once I put it on paper. I say, oh yeah, that looks strange. Let me not move an arrow that way, or let me not do this reaction first. Let me wait until later in the synthesis. Because with these benzene syntheses, you have to come up with the order of how to put in the groups, and it may make a difference. Sometimes it won't make a difference. It doesn't matter which group you put on first. Either way, it's fine. But other times, it does make a difference. So that's the molecule. You notice that you have two groups. Okay. I want to do trial and error, but I don't want to do a lot of scratch work. So my question is, well, if I go from benzene to nitrobenzene, so I'm covering up that second group, I could ask myself, how do I get on the second group? Okay. Well, if I do any electrophilic aromatic substitution now, this is a meta director. So I'm going to put a group in this position, the meta position, the one I'm pointing with my pink pen. The other meta position is over here. I don't get anything on the para position, right? Because nitro group is a meta director. So, okay, let's not do nitration first. Let's do something like this first. The thing is, oh no, like how do I get this group? This is neither bromination, nitration, sulfonation, free-to-cross alkylation, free-to-cross acylation. I know I have a bromine here, but it's not directly connected to the ring. So how do I do something like that? I have to put a methyl group and do NBS. The other question is, after I put on the methyl group, I know I could get this group by doing NBS. Does it matter whether I do NBS first, after the methyl, or do I do nitration and do this one first? Okay. Right now, I don't know. I need to see it on paper to see if there's any conflict or if there's any problem with that sequence. The main point is, if you do the nitration first, you're going to run into a roadblock because you can't put anything in that para position because this is meta-directing. So let me go the other way. Let me do the alkylation first. Okay. Oh, now I see. It doesn't matter if I do the nitration next because this is orthopara directed. But even if I put the bromine on there, it's still an alkyl group and I'll still be a good group. And the nitro group will go orthopara as well. So it really doesn't matter. Let me do the nitration next. So this is HNO3, H2SO4. So here's another point about synthesis. You know that this is orthopara directing. Okay? You don't have to draw both in synthesis. You just draw the one that you want. Okay? So because I could put the nitro group in the ortho position if I want, or the para position. But I want the para position because that's my target. Don't draw both is my main point. Okay. You've seen that before. When you make mixtures, you assume that you have the ability to purify that mixture to get what you want. Now, definitely, you're hoping that you're picking the major product. Okay, and this is the major product. The para is typically the major. And now we do bromination, NBS. BR, NO2. What could I have done next? Right? I could have made this once reaction longer by asking you to reduce this nitro group to a amine. I can make this one step longer by asking you to make this into an amide, right? To react with an acid chloride to make an amide. And honestly, that's how I'm going to make the syntheses. I have a big dartboard, and I have all the reactions for the benzene reactions, and I throw darts. And I say, oh, I wonder what they get if they do a nitration first, then a bromination, and then a sulfonation. I wonder what target they'll get and whether it's important that you do those in order. Okay, let's try another one. We have time. An interesting one is yes. This one is going to be a little bit subtle because there's going to be, we have to remember one of the Friedel-Crafts warnings. And one of the warnings is you can't do Friedel-Crafts on a ring that has a bad group, a ring that's been deactivated. So look at this example. Do that. This one right here. SO3H. This is 1, 2, 3, 4. Oh, it's this one right here. Meta to each other. Okay. This is where I'm going to do trial and error on paper to show you what possible roadblocks you might encounter. So let's do sulfonation first. If I do sulfonation first, which looks great, because I need a meta director, right? This is meta. So if I do sulfonation first, yeah, a meta director, I could put something in the meta position. So let me show you that. Fuming H2SO4, and I have this. Okay, oops, sorry. If I do this alkyl halide and AlCO3, and let's say you get the product you want, SO3H. Let's say this is an answer that I'm good grade. There are two issues to this. I'm going to say this doesn't work because there was a warning in the video that Friedel-Crafts doesn't work when you have a bad group, when you have a deactivating group. Okay, so it doesn't work with a deactivated benzene. So in this case, when I say deactivation, not only does it go slow, it actually shuts off the reaction. But that's only for Friedel-Crafts. You could do bromination on this. You could do sulfonation. You could do nitration. So you could do the other non-Friedel-Crafts reactions on this molecule here. Let me just finish this. Friedel-Crafts doesn't work with deactivated benzene. What is the other issue? The other issue is that this will rearrange. And you want to get 4 carbons in a row. So this synthesis has some issues. Maybe I'll give half credit for this. Okay, at least you knew that you did some type of Friedel-Crafts, some type of sulfonation. It's just the wrong order, but also you can't really use this alkyl chloride because it will rearrange. Okay. Well, we're in trouble because we can't do sulfonation first. Can we do this alkylation first? No, because an alkyl group is ortho-para directing. I would put the group on this carbon ortho or this carbon para. So how did that happen? How did I get a sulfonic acid in the meta position. So those are really difficult challenges because I've done both situations. I've added this first and roadblock. I've added this first, roadblock. The trick is this. You're not really adding an alkyl group first. What you're adding is an acyl group. And whoops, 4 carbons. And the clue there is you need to avoid rearrangement, okay? The rearrangement would put the benzene ring on the secondary carbon, not the primary carbon. One of the great things about acylation, and I think I might have mentioned this during class, is that it doesn't rearrange. If I didn't mention it in class, I definitely mentioned it on the video. So look at this. Does it really help us get to the product? You may not think so, because the product is an alkyl group, and I have a ketone. But the thing is, I know how to get rid of that using Wolff-Kishner or Clemmensen. So here's the other issue. Do I do that now? Do I do the reduction? Or do I do the sulfonation? This is already meta, so why don't we take advantage that this is a meta director and do the sulfonation now? It seems like there's a very specific sequence to do this synthesis, and any misstep will derail it. If you take any of these reactions in a different order, like we saw up here, you're going to run into some problems. You'll still get partial credit, but it does seem very specific that you have to follow this order exactly. And for Clemmensen, it's zinc mercury. For Wolff-Kishner, it's hydrazine. I'm actually partial. It doesn't matter which one you use, but I like Wolff-Kishner to get rid of that carbonyl group. This one is a good problem because not only does it show you that the order for some of these syntheses is super, super important, the directing effects are super important, right? To know why something cannot be done. Why is it better? Why do I have to keep this carbonyl group to do the sulfonation? Why couldn't I do the reduction first, right? Because now this is the orthopara director. So if I had waited for sulfonation, the sulfonic acid group wouldn't have gone in this position. It's a good problem because we have a side reaction, this carbonyl reduction. Okay, so this is not bad. I'm not going to be able to do many more, but take a look at this molecule here. What? How do I get a carboxylic acid? Well, that's one of your side reactions. Look at I didn't have to get you started with the methyl group there. I could have started you on benzene. But, okay, that's fine. If I know it's kind of small. I know I have a methyl group here. So what do I want to do first? Do I want to start putting these other groups? I'm going to assume that this carbon is this carbon. So I'm going to do an oxidation. But the timing of the oxidation is important. Do you want to do it now? Or do you want to do it later? Do you notice that this chlorine is ortho to this carbon, and this is para to this carbon? What I would do first is we have this methyl group here. I would put the tert-butyl group, doing Friedel-Crafts alkylation. And that way I would have a methyl group and a tert-butyl group. I know that this cannot be oxidized, right, because it has no hydrogen in the benzoic position. So this guy is safe. Okay? Oh. Uh-oh. Maybe I should put the chlorine first. Do you see what's happening? If I had put, oh, this is good. If I had done this next, okay, so I have these two groups on the ring. Do you realize that the molecule is confused about where to put the chlorine? Because both of these are orthopara directors, and they're in conflict because the ortho for the methyl is this carbon right here. The ortho for the terbutyl is this carbon right here. They're different. What should I have done first? I should have done chlorination first and purified the ortho. So I think I should have done this first, actually. Right? And then, why do I put the terbutyl group here? Because this is where you have the good, the bad, and the ugly. You have a good group versus an ugly group. The good wins. So you're basing the next reaction on the methyl group. And that's why this is para. Hopefully I put that in the answer key, that it's probably better to do the chlorination first. Once you have this molecule, yeah, just do the oxidation because you're not going to oxidize a terbutyl group. So that one's, I don't really, it's not the best problem because, well, I'm not going to say why, but that would be the preferred synthesis. Do the chlorination next and then the terbutyl group. Because again, if you have something like this, the directing effect is a little bit confused because these groups are both good, but they're telling you to direct the chlorination in different places. What are some other interesting ones? This one, right? You don't know how to do this directly. You have to go through the nitro group. Go through the nitro group, right? I wonder if this is. This is interesting too. Over here, you have two bromines, right? One is probably just bromination of the ring. The other one is NBS. But what do you do first? You notice that they're meta-directed. They're meta to each other. So this one's kind of screwy also, because bromine is an orthopara director. This CH2 group is an orthopara director. So I wonder how that happened, what we could do to get meta-directing. Okay. Let me give you one more problem. And it's this one here. This is not synthesis, this is fill in the product. Zoom out. See the dilemma here? Let me do, let's do nitration. That's the benzene ring on the left. Where are we going to put the nitro group? Here, 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 or here. Don't get distracted by the fact that these two groups are connected. Just isolate it. So if you have something like this, do you see how you have a good group on here? Good group for the oxygen. And you have a good group for the CH2 group as well. When you have competing groups, good beats ugly, ugly beats bad. But if they're both good, then very good beats moderately good. Where am I getting that from? I'm getting that from the idea that, see, this OR is very activating, but an alkyl group is weakly activating. Weakly activating. So we're basing it off of the good group at this position. Where's the orthopara? Orthopara. Okay. So I'm not going to draw you the answer, but that's my analysis. I have two good groups, okay, and I'm going to go with this one because it's more activating. It's very activating versus the alkyl group. Oh man, I had one more in my mind. No. Instead of that, I'm going to advocate that you please do the practice before the exam. Okay. I know it's open notes. Heck, you could even print out the answer key. But if you're searching, even if you have a couple hours, if you're searching and searching for an answer and you haven't done these yourself, it's unlikely that you're going to get full credit. Um, where's, where's one that's interesting? They're all interesting. But this one, very interesting. We see how you close the ring? This is an electrophilic aromatic substitution because you have a ring and you have an acid chloride. That's Friedel-Crafts. But do you see how it's nearby this carbon here? So you are doing an ortho Friedel-Crafts based on the ring attacking this carbonyl group. Okay. And they want you to fill in the reagents for each. So that's an interesting one. Next door. Sorry, let me just zoom out a little bit. Next door, number 9. That's an interesting one. Okay. Because now you're having to do the analysis that I did on the video, which is pretending that you have ortho meta para substitution and figuring out which one is the best situation. Do you remember this idea? This is where we proved that an oxygen is an ortho para director. Because in the ortho position for the electrophile, you have 4 resonance structures, but in the meta, you only have 3. You have time. You have more than 24 hours, actually, because your exam is due uh, tomorrow evening. Before I answer a couple questions if you have them, let me just show you what's on Moodle. I think you've seen all this already, but because the problems and the answers have been posted for a while. So here are your problems for 13 and your answers, and for 14 they're over here. Okay, practice problems and answers. What is new is there's one more extra credit, and it's actually this one right here. Okay. We have one more class tomorrow. So the plan is to have a review 10 o'clock on Friday, tomorrow, and then I will have the test already made up, fingers crossed. But I will give you your exam. I'll make it available at 11:30, and you have till what? You have till 8 p.m. Okay, 8 p.m. Friday. So if you can't do it after class, you'll have plenty of time. The extra credit, the last extra credit, I think, is this one. It's due today, 10 p.m. Just like your notes from Unit 14 are due today at 10 p.m. Okay. Let's read this together. Post one question or comment in this link, forum link, that you want me to talk about tomorrow at 10 a.m. It should be more than just, can you do number 7 on Unit 14? Put something like, I wonder why this position is favored for substitution when you said that atoms with lone pairs are orthopara. Or you could say, well, I came up with a new synthesis that I think that works for number 7. Can you tell me if this would get full credit or not? Okay. So give me something to work with. Just don't say do problem 2 or do problems 5. Only post one of those. Okay. So one each, please. If you have more questions, you could post it down here. Okay. I don't know if I'm going to give extra credit for the forum down here. I'm definitely going to give you extra credit if you post a good question or comment here before 10 a.m. tomorrow. Okay, and that way I'll have an idea of what are the last minute things that you want me to go over. Okay, The best strategy is to just go through the practice or go through the videos and just let me know what's confusing. Okay, what's confusing? There's 10 of us. I don't know if I'm going to get to every question, but if I don't, then I'll post the answer on the forum. But uh, I'll see if I could combine some into one topic. Oh, the other stipulation is I didn't read that. It has to be different than the others. Okay, so if you're the fourth person to post, read what the other three have said. It has to be a different question. You just can't be a repetition. Can't be a repeat. Okay, I'm losing my voice. Are there any? The chat is up, and this is Moodle. Are there any questions? It's a lot of material, but keep at it. The thing is, you do have time, or I assume you have time to master these topics. I wouldn't try to, like any subject, don't try to cram, especially for organic. It's really better to know maybe 75% of the material very, 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 very well instead of knowing all of the material 75% of the way. Okay? I think that's true for most classes. You want to master a topic, then move on. Um, okay. Oh, the lab. I have some lab stuff. Give me maybe a couple hours because your lab, I'm going to get it to you by today. Okay. The thing is, I don't think I'm going to be able to grade your lab 5, the lab that was due this morning. I'll try to put answers here. You could probably guess that I want to make sure that all of you know how to do a stoichiometry table and all of you know how to do limiting reactants calculations. So I'll post the answers for this later today. And this last lab is relevant to your exam because it's doing Friedel-Crafts alkylation. Um, there's a short video. I haven't put up the problems yet. I'm doing that right now. So give me some time. If I get this to you by this afternoon, it should be no problem checking your answers for Lab 5 and doing Lab 6 before the exam. Because I understand that if you wanted to get things done over with by tomorrow, you could have the lab and your lecture exam done by 3 o'clock tomorrow. Okay. But if you don't have time and you want to do some stuff on Saturday, the lab 6 will be due on Saturday. In the email, and then in the email that I sent a couple days ago, I'm giving everyone in lab the option to do a final exam. Those of you who had me last semester, summer session 1, that final exam was pretty comprehensive, right? It was 5 essay questions. I feel like, and this is totally up to you, I feel like everyone will get a fairly good grade just based on their post labs and their pre labs. But if you feel like you need the final exam to boost your grade, you got to tell me before. You got to tell me sometime today by email, okay? And then that final exam will be on Monday because I want to get all the lecture stuff graded as soon as possible. I think if you go through the syllabus, the notebook is worth 25%. The post labs are worth 75%. I think you could figure out what your grade will be based on the answer key and how confident you are with lab 6. All right. Are there any questions? You could raise your hand or you can chat. Jose's, using an email, Jose's office hours today are at 6 to 8 p.m. 6 to 8 p.m. And I think I did mention that my office hours will be after his. Let me just double check real quick. me 1 second. Oh, you know where it is? My bad. It was in the Wednesday notes. Let me check this. Ah, yeah. Tonight, 8 to 9. Um, I'll be in the room. You don't have to email me. Uh, if you have a question tonight, just hop on. It seemed like everyone was here, so everyone will get credit for coming to office hours because I said that the review session will count as office hours. Okay. All right. If there are no more questions, uh, you can leave, and I'll see all of you tomorrow. Okay. Maybe some of you later tonight. All right. I will catch you guys later.